Okay, so Jonathan, please.
Thank you very much. So I want to thank David for running the seminar, which I've enjoyed very much over the last year. When all the sort of in-person seminars are shut down, it's great to be able to see this. This is joint work with Eric Akkermans and Claude Schochet, who are both here today, I think, and also Slava Don, who I don't think is here, but anyway. Eric and Slava are physicists, condensed matter physicists, and Claude, of course, is another mathematician. So we're sort of taking the title at its word, a sort of mixture of mathematics and physics here. And this work just came out in the Journal of Geometry and Physics within the last month or so. So let me start by talking about quasi-crystals. So all of you are familiar with crystals. Those are solids with a very regular periodic pattern. A quasi-crystal is an ordered solid that's not periodic, even approximately. Now, true crystals, as you know, are not 100% periodic because they have small crystal defects, but that's a kind of minor perturbation on the structure. But quasi-crystals are not periodic in any sense. And they were sort of first discovered back in the 1980s, and they were recognized in the Nobel Prize in chemistry, which went to Don Schechtman in 2011. And this is a picture taken from Schechtman and Bloch's original paper in Metallurgical Transactions in 1985. So they took an X-ray diffraction pattern from an aluminum manganese alloy, and they saw this picture. Now, when you first look at this, you'd say, this is just a sort of typical X-ray diffraction picture of a crystal. But when you look at it carefully, you see that it's not, because, for example, over here, you see a regular pentagon. And over here, if you look at the dots surrounding the central dot, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. They sort of are arranged in the pattern of a regular tengon. But you're probably all familiar with the classification of the three-dimensional crystallographic groups. And there's nothing that has 5-fold or 10-fold symmetry. So this cannot be a real crystal because you can't get this kind of a pattern out of a real crystal. So on the other hand, it looks so regular. When you first look at it, you're almost convinced that it is a real crystal. So what's going on here? So that's really the puzzle. Okay, so in an actual crystal, or at least a sort of idealized model of one, Bloch's theorem says that you can expand the electron wave functions into things that look like a plane wave times something that's periodic. And here, so R is the parameter in the crystal, and K basically lives in the dual space. This is what's usually called the quasi-momentum, I guess. And so so you get an expansion in terms of things like this, and this K runs, if your original crystal is, let's say, is in the form of a regular lattice, then the K runs over the dual lattice, the dual lattice in the dual space. And that the dual space divided out by that dual lattice is what's called the brion zone. Now, when you look at the X-ray diffraction pattern, you see these sharp peaks there. You can see the picture even in the case of the quasi-crystal. And those are called the Bragg peaks. And they're characteristic of the crystal structure. And so by looking at the diffraction pattern, you can sort of figure out what the shape of the crystal is. And then you also have the energy spectrum, which can be understood in terms of the density of states. In other words, how many states there are with certain energy levels. And what we're going to try to talk about today is to try to discuss how you can find analogs of all these concepts from classical condensed matter physics for non-periodic materials like quasicrystals. And while there are lots and lots of people who have worked on this, including quite possibly many of the people here at the seminar, I hate to slight people. I think it's fair to say that the main developers of this subject were Jean Bellissardand and ultimately Alain Kahn, who introduced the idea of non-commutative geometry and how it could be applied to problems like this. So the idea is to replace the classical geometry of the brion zone, which in the sort of classical case is something like a torus, with non-commutative geometry. So in the simplest examples, what you get is a non-commutative torus, and you can get more complicated examples also. So that's the basic idea. Now, we need a kind of mathematical model for a quasicrystal that replaces the usual model of an ordinary crystal. And for that, we're going to use tilings, which are more flexible than crystals. So you can think of a crystal as being a periodic tiling, and we're going to talk about non-periodic tilings. So you have tilings of, let's say, Euclidean space of dimension D by polytopes, which are called tiles, and they satisfy the following sort of standard axioms in the usual model. So first of all, we assume there are only finitely many types of tiles up to translations, and each tile can occur in only finitely many orientations. So again, since this was all motivated by trying to understand the structure of things like metallic alloys, you know, you can think of these tiles as being the shapes taken up by atoms in certain energy states or certain molecules, that sort of thing. Okay, so you have finitely many types of tiles. Let's say in that example back here, you had aluminum and manganese, and each tile only occurs in finitely many orientations. And the tiles cover the whole space, and two tiles are assumed to meet full face to full face. So you can think of the tiling as something like the arrangement of a floor in a bathroom, you know, where you take tiles of various shapes and paste them together to cover the floor. And we'll also assume that we have finite local complexity, which means that in a ball of fixed radius, there are only finitely many configurations that can occur up to translation. So that's satisfied, for example, for something like the Penrose tiling and many other examples that you're probably familiar with. So given a tiling like that, then you can form the associated tiling space, which is the collection of all possible tilings that can be formed from the same tiles with the same allowable configurations. And so that every local patch of one of these tilings is a translate. Sorry, one of these should not have a prime on it. Every local patch of T prime is a translate of a patch of T. So there are certain basic configurations, and they repeat at irregular intervals, and you're allowed to slide things around. So you're allowed to move things under translation. So R to the D acts on omega by translations. And the finite local complexity assumption implies that this omega is compact. And it turns out there's sort of interesting theorem of Lee, Moody, and Solomiak from 2002 that in the case of what are called Delaunay multisets, which is close to the situation that one almost always has, then then unique ergodicity of this situation, in other words, the existence of a unique invariant measure under this RD action is equivalent to uniform cluster frequencies. So uniform cluster frequencies means that if you take any particular configuration, it recurs in the tiling at a certain fixed rate. Okay, so then under all these sort of basic assumptions, which are just sort of standard in the theory these days, there's a theorem of Sadoun and Williams that tells you what this omega looks like. Remember, we said up here that it was a compact space. So it turns out it's homeomorphic in a way that preserves the RD orbits, though it's not necessarily an equivariant homeomorphism, but it's at least an orbit preserving homeomorphism to the total space of a fibration where the base is a torus and the fiber is totally disconnected. Now, if the fiber were just a point, that would say that omega is t to the d, and this is exactly what you would get from a periodic tiling based on a lattice. And for other kinds of crystallographic groups, this n is finite and you still get something like this. But when you have a non-periodic tiling, then typically this n is a Cantor set. So the omega is compact, but it's definitely not a manifold. It fibers over a torus, but the fiber is typically a Cantor set. And then, of course, r to the d acts transitively on the base here by translation, and the r to the d orbits are what you get by lifting up the. So if you take a point in omega, it has an r to the d orbit, which lies over this torus down in the base. But upstairs, the orbit may not be periodic. It can sort of loop around and come back, in funny ways like that. Okay, so now we want to understand the geometry of this omega. And the best way to think about it is as a foliated space. So over here, I said that omega's homeomorphic in an orbit preserving way to something like this. So it turns out it won't be any loss of generality to assume that omega is actually n induced up. So this n carries a z to the d action, which is the fundamental group of the base here. So the base here is a torus. Its fundamental group is z to the d, and that fundamental group of the base acts on the fiber. So you have a z to the d action on n, which is typically a Cantor set, and then you induce up that action to r to the d, and that's what omega looks like. So anyway, without great loss of generality, you can always assume we're in this situation. So n is a Cantor set, and you have this z to the d action on n, and then you induce it up to an r to the d action. That's what omega looks like. So here's a basic theorem. If you try to compute the Čech cohomology of omega with coefficients in either z or r, what you get is the group cohomology of z to the d. Remember, that's acting on n, so it acts also on the functions on n. So take the group cohomology of z to the d acting on the C infinity functions on n with values either in z or r. Okay. This thing will be non-zero only for k between 0 and D, and it vanishes in the higher degree. And in top degree, the top degree cohomology is the same thing as the co-invariants of Z to the D acting on C infinity functions. I should say, if you're not familiar with this terminology, on a totally disconnected space, a continuous function is called C infinity if it's locally constant. And that's the standard terminology that comes up in analysis on p-adic groups. Since p-adic groups are totally disconnected, you need to deal with functions like that. So, so that's what we mean over here. Okay, so for example, if G is equal to Z, C infinity of n with values in Z is just the locally constant functions and with integer values. And if G is equal to R, it's locally constant functions with real values. So now we understand the cohomology of omega. And now some other invariants are going to come into play. So this omega as a foliated space is locally homeomorphic to X cross R to the D, where X is totally disconnected. So X is just a little, like a little patch of that N. From the action of R to the D on the second factor, you have the foliation, and we have an invariant called the tangential cohomology, which is the cohomology of the tangential de Rham complex. So those are forms which are smooth in the leaf direction. So the leaves of the foliation, remember, are manifolds. Those are they're locally homeomorphic to R to the D, so it makes sense to talk about differential forms that are smooth in the leaf direction, and in the transverse direction, we just require them to be continuous. And you can think of this as the sheaf cohomology, the sheaf of germs of continuous functions that are locally constant in the leaf direction, whereas the Czech cohomology is the sheaf cohomology of the constant sheaf. So there's an obvious map from the constant sheaf to that other sheaf. So that induces a map on cohomology from ordinary Czech cohomology to the tangential cohomology. And here is a comparison theorem that sort of explains the difference between them. So this comparison map between the two cohomology theories can be identified with a map on group cohomology for the group Z to the D acting on C infinity of n and C of n respectively. So Czech cohomology, remember, was the group cohomology of C infinity functions, and tangential cohomology is the group cohomology of continuous functions. So this map over here, of course, is an inclusion with dense image, but just because a map here is inclusion, it doesn't mean that the map on cohomology is necessarily injective. But what is true is that this map over here, inclusion of C infinity into C, has dense image. And so the inclusion of the Czech cohomology, we'll call it inclusion even though the map may not be injective. So you map from Czech cohomology to tangential cohomology. That map always has dense image for the natural topology on this thing, but unfortunately the natural topology on this thing is not always Hausdorff, so you have to be careful about that. It's what Cal Moore called an almost Polyné group. So it's, it has a natural topology and it's a quotient of something which has a nice topology, but it may not be Hausdorff. So to use this foliated geometry to get numerical invariants, I mean, to go back to the original physics, we're trying to compute things like the integrated density of states or some other invariants of the quasi-crystal that's based on this tiling space. So we need a way to integrate on omega. And the correct concept is that of an invariant transverse measure. So if you think of omega this way, that's the same thing really as just a z to the d invariant measure on n. And the invariant transverse measures can also be identified with linear functionals on the maximal Hausdorff quotient of the top degree tangential cohomology. So that means we just want linear functionals on C of n. Those are just ordinary measures on n, which are invariant under z to the d. And in the case of uniform cluster frequencies, as we mentioned, then the action's uniquely ergodic, and then there's a unique such measure. And that's what we always use for integration. So in that situation, this cohomology group is actually one-dimensional, and the comparison map is surjective. So then this actually has to surject onto that. Now, attached to an invariant transverse measure, this is a sort of more general concept from the theory of foliations. There's something called the closed Ruel-Sullivan current, and that defines the class in the Hausdorff continuous dual to the top degree tangential cohomology. So this is in top degree tangential homology. And this homology group can be identified with the vector space of the signed invariant transverse measures. In the uniquely ergodic case, this thing is one-dimensional, and that invariant transverse measure is actually, if you normalize it correct, it's actually positive. Okay, so now let's make the assumption, which is satisfied in all cases of interest, that the holonomic cover of each leaf in omega is simply connected, so that the foliation Cstar algebra, which involves the holonomy, is just the same thing as the cross product of C of omega by r to the d. So this is called the foliation Cstar algebra. And it's basically just the transformation group Cstar algebra for r to the d acting on omega. And since the r to the d action was induced up from the z to the d action on n, this thing over here is Moridi equivalent to this simpler algebra, which is unital. So you have C of n, this n typically think of as being a Cantor set, and you have z to the d acting on it by something like a subshift or something like that, and then you take the cross product. And by Kahn's Thom isomorphism theorem, if you want to compute the K0 group of this Cstar algebra, that is isomorphic to the K theory of omega, let's say in degree d. All right, the d could be either odd or even. So this could be either odd or even though we're mostly interested in K0 because we want to pair with traces which give linear functionals on K0. So now, if you fix an invariant transverse measure, let's say nu, then you have this Ruel-Sullivan current, and you also have a trace on the foliation Cstar algebra. So you have a so-called K-theory trace, which is a map from this K0 group to the reals, which you can think of as basically being computed on this unital Cstar algebra over here. And then if you have a projection in this Cstar algebra, this just computes the dimension of that projection with respect to the trace. But you can also think of this as a a map from k to the d of omega into the reals. So that's the K-theory trace. And then you also have the cohomology trace, which is just pairing of tangential forms with the Rayleigh-Sullivan current. So that's just a linear functional on tangential cohomology in top degree. So we have this trace over here, and we have the trace on the Cstar algebra. And in principle, these are totally different things. But if you use the, if you use the Kohn and then the Kohn-Skondalis index theory for foliations, then what comes out is that you get a commutative diagram like this. So these two traces are actually closely related. Over here, we have the K-theory trace. So that's defined on K0 of the Cstar algebra. Over here, we have the cohomology trace. I've written it as being defined on the Czech cohomology. Now, originally, the Rayleigh-Sullivan current pairs with the tangential cohomology, but we also have this comparison map that goes from the top degree Czech cohomology to the tangential cohomology. And remember, in the uniquely ergodic case, which is a case of most interest, then this thing is actually surjective. So this, you can pull back the cohomology trace on here to the Czech cohomology, which is a little more computable. Because this is just a topological invariant of omega, right? So this is fairly easy to compute. So you have the cohomology trace defined on the Czech cohomology over on this side, and you have the K-theory trace on the K-theory of the Cstar algebra on that side. Now, what is it that relates these? Well, this phi is the inverse of the Kohn-Thom isomorphism map. So you can, if you take the inverse, the natural map really goes the other way, but you can define the phi in terms of index theory going this way. So, so that there's a KK class that you can write down explicitly that gives rise to this. So this is the map from K theory of the cross product to K theory of omega. Omega, remember, is just a space. So this is just ordinary topological K theory. And then you can apply the top degree part of the Chern character, which sends K theory to cohomology. And that's what the CH sub D is. So that's we've called it the partial Chern character because the Chern character really has components in many different degrees. So we're only interested in the component in top degree. All right, so when you study the index theory for foliations and you translate it into what it actually means, it comes down to this. So, all right, so now we know about the K-theory trace and the cohomology trace, and they're related by the Chern character, et cetera. So now let's go back to the original physical problem. So we wanted to try to understand the material properties of a quasi-crystal in terms of this mathematical model. And those are governed by the spectrum of the Schrödinger operator, which has a kind of quasi-periodic potential based on the underlying tiling. Well, quasi-periodic actually has a technical meaning, and there are going to be some tilings for which this thing is technically quasi-periodic, in some cases where it's not, but I'm just using this word kind of loosely here. But in any event, given the tiling, that sort of determines the arrangement of the atoms in this quasi-crystal, then you want to understand the spectrum of the Schrödinger operator, and that's what's going to determine the material properties. So we want to know about things like gaps in the spectrum, because those determine the conduction bands, the magnetic properties, the specific heat, etc. All the things that you usually measure in a laboratory when you want to understand material properties of something. So this we will call the dynamical spectrum. And the observation, which I guess originally goes back to Bellissardand, is that if you take the bounded continuous functions of the Schrödinger operator, they will live in this tilings Cstar algebra. So therefore, if you take spectral projections associated to any pure point spectrum that happens to exist, then those are projections in the Cstar algebra, and so that's why the K-theory trace is relevant. You want to understand K0 of the Cstar algebra and its image under the K-theory trace. So that will give you the dimensions of these projections that identify points in the pure point spectrum. So that gives rise to the so-called gap labeling problem, which is to try to understand what the K-theory trace looks like very specifically on K0 of the Cstar algebra. And in principle, if you understood this thoroughly and you know what the Schrödinger operator looks like, then you can go ahead and make explicit calculations. Now, there's another kind of spectrum which is also relevant, and that is to try to determine what the Bragg peaks are. So that's the diffraction spectrum, and that basically measures the dots that show up, when you take an X-ray diffraction picture. So that's not quite the same thing as the dynamical spectrum. So this spectrum and that spectrum are related, but they're not the same. So in general, they don't coincide. Okay, so ultimately, what one would like to be able to compute are all these material properties which involve the dynamical spectrum and the X-ray diffraction spectrum, which determines the Bragg peaks. Okay, so that's the basic physical problem, and that's the mathematical model. Okay, so now a step toward organizing this, which was originally based on explicit low-dimensional calculations, was Bellissard's gap labeling conjecture. And that says the following. Suppose you have an invariant transverse measure and you have the associated K-theory trace. So you can think of that as lying on this Cstar algebra or on the Moridi equivalent unital algebra. This algebra over here, of course, is just this algebra tensored with a compact, so it's easier to compute on the unital algebra over here. So the image of the K-theory trace, according to this conjecture, coincides with its restriction to the abelian subalgebra C of n, which would just be nu applied to the, well, n is totally disconnected. So K0 of n is just the same thing as H0 with integer coefficients, which is just, if you like, it's just the continuous functions from n into the integers, the locally constant integer valued functions. And then you apply nu to those, and that this thing, of course, is a subalgebra of the cross product, but in general, the cross product is a lot more complicated. So there's no reason why the trace on the whole cross product should coincide with its restriction to this subalgebra. So in some sense, this conjecture is a bit of a surprise, but it was borne out in a few examples, and that's what led to the conjecture in the first place. So once again, the gap labeling conjecture says that the K-theory of this cross product, when you apply the K-theory trace to it, has the same image as just the restriction of the trace to the abelian subalgebra inside. Now, this was proved by Bellissardand and his collaborators for up to dimension 3. That was back in, I guess, starting in the 1980s and going up to around the year 2000 or so. And then around 2003, there were 3 papers written independently and simultaneously that were published claiming a proof of the general case of the conjecture. And I hope Claude, you don't mind my mentioning that Claude Schochet, my co-author who's here on the seminar, wrote a featured review of these 3 papers in Maths.net that explains how they got this great result of proving the general case of the gap labeling conjecture. And each one of the proofs has useful intermediate steps in it, but they all contain the same underlying mistake. So the correct statement is actually not this, but what follows. So we don't claim any great originality for this because I think this has pretty much been known in the community of people who work on this subject for the last 20 years. But anyway, from the main theorem that I stated before, you can get the following consequence. So the image of the K-theory trace, which remember is what the gap labeling problem is all about, coincides with the image of the cohomology trace, not on the integer cohomology, but on the image of the K-theory under the Chern character. Now, this is a kind of a subtle thing because the Chern character, after you tensor with the rationals, is an isomorphism between K-theory and rational cohomology. But if you look at the Chern character on integral cohomology, it doesn't usually go into integral. If you look at the Chern character on integral K-theory, it doesn't usually go into integral cohomology. It goes somewhere into the integral cohomology, and it lands on some lattice inside this thing. And it's not always clear what lattice that is. Now, there are compact spaces for which the image of the Chern character actually lands in integral cohomology. For example, that's true for spheres. That's a famous theorem, which you can prove using the Bott periodicity theorem. So the Chern character sends the K-theory of a sphere into and in fact onto, it's actually an isomorphism, onto the integral cohomology. But for most spaces, it just lands in the rational cohomology and there's some denominators. So what is true is that if the Chern character happens to land in the integral cohomology, then the gap labeling conjecture holds. But if the image of the Chern character is not equal to the integral cohomology, then probably the gap labeling conjecture is false. So that theorem basically reduces the gap labeling conjecture to a problem in topology, namely, for tiling spaces, is the image of the Chern character in integral cohomology or not? So you can check that that's always true for d less than or equal to 3, but that's because for all compact spaces, the image of the Chern character lands in integral cohomology for d less than or equal to 3. But there are spaces of dimension 4 and up for which the image of the Chern character does not land in integral cohomology. For example, this is already true for CP2. That's the simplest example I can think of. Because S4, for example, for S4, it does hit integral cohomology, but for CP2, it doesn't. So, so far, nobody's written down an explicit example of a tiling space with non-integral Chern character. but I strongly suspect that such things exist, and I even have a kind of a program for trying to generate such an example. It's just that the calculations are fairly complicated, haven't done it yet. So I suspect that the gap labeling conjecture is actually false, but it's not false by all that much because you can control the denominators in the Chern character. So you can give the following statement. So the top degree part of the Chern character is integral after you multiply by basically d over 2 factorial rounded up. So well, the d over 2 is rounded up, and then you take the factorial. So it means you don't miss the integral cohomology by all that much, but you, in general, do miss it. So this is not using anything specific about tiling spaces. This is just a general fact about the Chern character on compact spaces in general. This just comes from the definition of the Chern character. But whether tiling spaces are different from general compact spaces or not is not totally clear. I mean, there are some restrictions on what kinds of spaces you can get here, but what the Chern character looks like on them is still not totally clear. Now, that's about it for the general theory. Thanks to my physics collaborators, we have some specific calculations for one-dimensional tilings. And since the gap labeling conjecture is true up to dimension 3, there's no problem with that in this situation. And case of 1D is particularly easy, and also it's particularly amenable to experimental tests because it should be possible to manufacture materials based on one-dimensional tilings and actually test various material properties to see how the theory agrees with experiment. So if you have a one-dimensional tiling, let's say you have an alphabet of 2 letters, so there are 2 kinds of tiles, A and B, and a tiling is just a sort of infinite string of these letters. So, you can do explicit calculations of the Čech cohomology and the diffraction spectrum. There are 2 kinds of 1D tilings that have been studied in detail. They're the so-called cut and project tilings, and they're the substitution tilings. So for the cut and project tilings, this is a picture from a paper by Julien in Ergodic Theory and Dynamical Systems in 2010. The way you get a cut and project tiling is that you start with a periodic lattice, and you draw a little strip inside it. That's the strip bounded by these 2 dotted lines. And then you look at all the lattice points inside that strip, and you project them down orthogonally onto some subspace, which in general is sitting inside there at some kind of irrational slope. Okay, so we take these points that are inside the band and we project them down. So first we cut down to what's in the band, and then we project onto the subspace. And then you see that they're arranged in something that looks almost periodic, but it's not. Okay, because of the fact that the slope could be irrational here. So that's one kind of, and then there's a recipe for translating that distribution of points into a tiling. So that's a sort of cut and paste situation. Another kind of tiling are substitution tilings, where you start with a word in your alphabet and you make repeated substitutions according to some rule. Like, for example, every time you see an A, you replace it by ABA. Every time you see a B, you replace it by AB. Then you do this again, you do it again, and do it again, etc. And then the main properties of the tiling are determined by eigenvalues of the substitution matrix. So you just ignore the order of the letters here. And let's say that your substitution sends A to something with alpha A's and beta B's, and it sends B to something with gamma A's and delta B's, ignoring the order. So in this example here, A goes to something with 2 A's and 1 B, so that gives us a 2 and a 1. And B goes to something with 1 A and 1 B, that gives us a 1 and a 1. And so this is a unimodular matrix with determinant 1 and irrational eigenvalues. So this is a sort of typical example of substitution tiling. So here are some calculations for a representative set of these one-dimensional tilings. And here we've indicated the Čech cohomology. That's in this column of the table. And the diffraction spectrum. So this is what you'd see if you were to take an X-ray diffraction picture. So this tells you where the peaks are. And this tells you the nature of the diffraction spectrum, whether it's pure point, that's PP, or absolutely continuous, that's AC, or singular continuous, that's SC. And you see you can get all sorts of different kinds of behavior. Also, one thing that's interesting to note when you look at these things is that the Čech cohomology in general is not finitely generated as an abelian group. So it's quite typical to get things like the dyadic rationals. And that comes up in many of these sort of classical tilings. So Čech cohomology in general is fairly complicated. In these first two examples, of course, for periodic tiling, the tiling space is just a circle. So of course, H1 is equal to Z. The Fibonacci tiling corresponds basically to an irrational rotation algebra. So that's a non-commutative torus. But then these other cases are more complicated. And this is sort of what the diffraction peaks look like. So you would see this if you took an X-ray diffraction picture. In this case, there are no peaks because you have a continuous spectrum. And this lambda over here that showed up in the Fibonacci example is the golden ratio. So here's some, and for those same examples, here's the calculation of the range of the trace. So in this case, I don't have to say whether it's the range of the K-theory trace or the range of the cohomology trace because they coincide. So in the periodic case, it's the obvious thing. Fibonacci case, it's also the obvious thing, and that's because the trace, there are two generators here. The trace assigns dimension 1 to one of them and dimension 1 over lambda to the other. But in the other cases, you get something kind of peculiar. Notice this factor of 1/3 out in front. And also notice that in the Rudin-Shapiro case, the trace only sees this part of the cohomology. This part doesn't really seem to show up. Okay, so cohomology is much bigger than the image of the cohomology under the trace. And that's basically because these things get collapsed to just a single copy of the dyadic rationals when you apply the trace. So the trace doesn't have to be injective. So here's some calculations for those 1D tilings. Let me just conclude by showing you a few pictures. So here's the energy spectrum for a sort of discrete approximation to the Schrodinger operator. So this is a case of a periodic tiling And you notice there's a fairly regular spectrum with these horizontal bands here at a certain fixed energies. And then there's a sort of nice, smooth counting function that interpolates between them. But for the non-periodic tilings, this is the Fibonacci tiling, and this is the 2A Morse tiling. The energy spectrum and the counting function, well, the energy spectrum is more fractal looking, and the counting function tends to look something like a Cantor function. So it's, you know, something like this, which is very irregular, even though it's continuous. So the nice thing about these 1D toy models is that, as I said, you can do explicit calculations of everything for them. And also, presumably, you can manufacture them in a laboratory and test that these things agree with the experiment. And if you want to know about the lab experiments, you should talk to Eric. Okay, so I think that's about it. That's 52 minutes. So I'll stop there and happy to answer any questions.